So this is Chapter 8, Covalent Bonding. I'm going to try to make this brief and get through things quickly, so if you need to go back or you have questions, just please let me know. Some of the objectives, we want to apply the octet rule to atoms and look at how they will form covalent bonds due to the octet rule. We're going to talk about how single, double, and triple covalent bonds form, and strength of a covalent bond to its bond length and bond dissociation energy. We'll talk about all those terms, so don't go crazy thinking about them right now. Okay, and then we have more than just chemical bond as a review vocabulary, but that'll be a term you want to know for this section. So some new vocab: covalent bonds, molecules, Lewis dot structures, endothermic reaction, exothermic reaction. The main idea is all about stability. Atoms form covalent bonds because they're seeking to be stable as a compound, and seeking to be stable as atoms, and so they form compounds. We'll talk more about that. So atoms are going to gain stability when they share electrons to form those compounds, and that specifically is what we look at in covalent bonding. But if you remember from last chapter, ionic bonding, they also are seeking stability, but they're not sharing. So being stable means that you're in the lowest energy state, okay, a lower energy state. So whenever electrons are in their lower energy state, they are stable. So essentially it's almost like gravity, right? Everything wants to fall to the ground. Everything wants to be the closest to the center, to the nucleus. So let's real quickly just review what's an ionic bond. So when we gain or lose valence electrons to become stable, atoms will get to a noble gas electron configuration. So they want to be like the noble gases. Most cases, that's going to be having 8 valence electrons. So either they do that by gaining them, which we see the increase in size, and those would specifically be our nonmetals. Nonmetals are going to gain electrons. What would their charge then be? Yes, it would be negative, because now they have more negative particles. On the other hand, valence electrons on metals are going to lose those electrons, so they're going to decrease in size, and they're going to become positively charged. I don't know what did that. So a blank is formed when 2 or more atoms bond. A bond, right? A bond is formed when 2 or more atoms bond. The chemical bond that results from sharing electrons, though, that is called a covalent bond sharing. Form bonds to get to an octet, right? So there are exceptions. Some are going to seek what we would call a duet, and so that means that they just want 2 valence electrons in their outermost energy level. Reason being, they are closer to just having that lowest energy level filled, right? So that's either a few metals that will lose, or hydrogen, which will gain, and then obviously just specifically the noble gas helium, which has 2. So real quickly, hydrogen, helium, lithium, and beryllium, those are the major ones that are exceptions. There are other exceptions. I'm not going to talk about them. So there's some that they'll form, like they'll want to get to 10, or they'll want to get to 14 or 16. Those are weird guys. We're not going to talk about them. So sometimes elements bond to themselves. Okay, so when they do that, they're going to bond element to element of the same, or atom to atom of the same element, and this is called a diatomic molecule. They exist because these 2 atom molecules are more stable than single atoms. The chlorine atoms, iodine atoms, fluorine atoms, hydrogen atoms, bromine atoms, oxygen atoms, and nitrogen atoms all form diatomic molecules. A way to remember all these diatomic molecules is the mnemonic Cliff H. Braun. Now, if you look at these real quickly, which group are most of these elements in? If you look at a periodic table, you'll notice that the majority of them are in the halogens, or group 17. That specifically is one where they form diatomic molecules. So we call, when one pair of electrons is being shared between 2 atoms, we call that a single covalent bond. Some examples: hydrogen and fluorine are elements that are going to form that. Now, why would hydrogen only share one pair of electrons with something? Well, look at its electron dot structure, okay? Same with fluorine. Why would it only share one pair of electrons? Well, if you look at both their dot structures, they each have room for one more, right? Hydrogen wants to form a duet, so it just wants to share one electron with something and something else share its other electron with it and form a duet. And then fluorine, one electron here would satisfy its octet, and so it's often going to it's only going to form a single covalent bond, okay? If you remember, if we went back, those are also both elements that form diatomic molecules. So hydrogen will bond to itself in nature. Fluorine will also do that because they want an octet. So the halogens, the group 17 elements, they all have 7 valence electrons. So they're going to form those single covalent bonds with other atoms of nonmetals, okay? And then this is just maybe for your own benefit to draw the electron dot structure for a halogen. Draw a second of that element. Notice that they form diatomic molecules. Okay. 16 elements, they're going to share 2. Think about it. If you have oxygen, for example, it has 6 total valence electrons. Okay, and so because of that, it has 2 locations where it can bond to something. So let's look at water, for example, right? If you drew water, you'd have the oxygen in the middle, and then it would have its 2 valence electrons on top, 2 on the bottom that are the lone pairs, and then you could put 1 on each side. And then guess what? If a hydrogen comes in on both sides, they're going to form single bonds on both sides. So they form 2 single covalent bonds. Atoms in group 15 may form 3 single covalent bonds. So if I put nitrogen, and then I were to put its valence electrons, the pair on top, and then once I have 1 pair, I only have room for 1 single one on each side, because you need to at least have 1 on every side before you, at least when you're initially drawing it, before you can stop. And so then each side could bond with 1 hydrogen, except for the top where there's that double bond already, right? And that would give you ammonia, NH3. Group 14 elements form 4 single covalent bonds. So carbon and methane is a good example. If I draw carbon and I put a valence electron on each side, that's all its 4 valence electrons. Guess what? If I draw hydrogen on each side, it can bond to singly with each side of the carbon, okay? Now, which group do you think has elements that bond the most covalently? You know, think about elements and their bonding like friends, right? Which of those elements is most likely to be happy by bonding with a lot of elements? Let's go back for a second. Oops, sorry. Carbon is in group 14. It wants to form 4 single covalent bonds. It's bonding with 4 different elements. Group 15, 3. Group 16, 2. And group 17, just 1. So of those 4, which one bonds it the most? Carbon. So elements that are in the group 14 are going to be most likely to bond with more things covalently. Okay, let's talk about multiple covalent bonds. So if we talk about double bonds, right? A double bond is when there's 2 pairs of electrons shared between 2 atoms. So if I have oxygen next to oxygen, right? Remember, oxygen has 6 valence electrons. Well, if I just try to do a single bond between oxygen and oxygen, they're not happy. Because guess what? Since each has 6, when they put that one in the middle next to each other, you actually end up with 7 around each oxygen, which doesn't make them happy. So you actually have to bring in both of those single electrons and give 2 on each side. And once you give 2 on each side, guess what? Oxygen is now going to have 8, and this oxygen would also have 8. And triple is when you have 3 pairs of electrons being shared. So an example is nitrogen. Nitrogen will bond to itself in a diatomic molecule, sharing 3. Since nitrogens both have 5, together they can just share 3 of their electrons in the center. And that's 6 total electrons in the center. Since they already are sharing 3 on the inside, guess what? There's 2 on each of them on the outside of their atom when you draw in their electron dot structure. And that makes them happy. Okay, real quickly, let's look at bond strength. So strength of a bond is dependent on the distance between the two nuclei. So the further apart they are, the weaker it is, okay? So as length increases, strength is going to decrease. So here's fluorine. It's got a single covalent bond. Look at that bond length, 1.43 times 10 to the negative 10th. That may not look like much to you, but if you thought about that, you know, this is a very tiny number. With O2, we got a double covalent bond. Although this is still a really tiny number, 1.21 is actually times 10 to the negative 10th is actually a little bit shorter than this bond, okay? And then triple covalent with this nitrogen is going to be even a little bit shorter. If you want to do a little quick home experiment to affirm this or to kind of visualize this better, use a rubber band, okay? I want you to take a rubber band and stretch it out until you're afraid it might snap. Has its strength increased or decreased? Okay? Then do the same thing, but double it up. So kind of twist it in the center and pull it apart where you have a thickness of 2 of the rubber band on both sides, right? Does it feel like it's stronger? Is it harder to pull it apart? Has its length increased or decreased? And then do it one more time. Turn it around in the center and pull it a third time so you have 3 sections of rubber band on both sides. Is it harder to pull apart? Has its length increased or decreased? Okay, so you can try that as a good way to test this and to see it visually if that's helpful. So what we call the amount of energy required to break the bond between those two atoms, once you have that bond, right, that has to be chemically broken apart. We call that bond dissociation energy, okay? When you think about it, to dissociate from something, okay, to associate is to come together, right, or to be around people, right? It's funny because we're practicing social distancing, right? So distance, if you're associating, you're coming together. If you're distancing or dissociating, you're coming apart, okay? So the shorter the bond length, the greater the amount of energy to break it, right? So if you remember fluorine, it has the longer bond length, so it's actually easier to break it apart. It takes less energy, okay? Oxygen, it was closer together, so it now is going to take more energy than the other one. And then finally, nitrogen is a really good bond, really hard to break apart, okay? I wonder if that has anything to do with why there's so much nitrogen in the atmosphere. So when bonds are broken and made, they are either going to take in or release energy, okay? If they take in energy, then that would be considered endothermic. And so those reactions lead to a cooling effect, okay? We did this in a lab. I don't know if you were there to do this lab. Whereas exothermic, they're going to release, right? They're going to produce more energy and release it to the environment, which means you have a heating effect. So exothermic is something like combustion, something where there's an explosion, right? Endothermic is something more like the way dry ice reacts with the environment, okay? And so it's going to be cooling off or getting colder. Ice packs work this way, right? Okay, and endothermic, exothermic, that's kind of how we do our different, those different heat packs and cool ice packs, okay? Here's just an image to kind of show you how that works, right? But the activation energy is the energy at which you start to actually see a reaction occur, okay? And I'm going to stop there. That's 8.1. It's a really important section, so I don't want to jump into 18.3 yet. I would like you to kind of just review that and to, if you have any questions, to let me know. And I'm going to see if I can get you some specific questions. If not, I'll just give you them as like a whole quiz over the whole chapter.